So a little bit about what we do. I look at ultra-fast electronic dynamics, and I look inside photosynthesis. It's about solar light harvesting, so the NREL type of example that we heard about before is really on point. We look at how plants have evolved to make use of quantum mechanics in their light harvesting. That sets some boundary conditions. It means you're going to have to look at things at a molecular level. It means that the time scales that you're going to look at are femtoseconds. So that's a millionth of a billionth of a second. So if you think about the speed of light, that's about the time it takes the speed of light to move 300 nanometers or a third of a micron. So that means that all of your distances, your timings, your scales, they have to be about 1 million times faster than the fastest computers, roughly. And that's hard, as it turns out. That also means that if your laser table expands or contracts by a micron, you're done. You really need to keep it stable. It also means that if humidity changes and changes the index of refraction, that changes the time it takes your light to propagate down the laser table, and you're done, and things aren't going to work. Now, there are ways around that. You can try and stabilize everything actively, but then your students become electrical engineers and you never get any work done. And the biggest issue becomes one of productivity versus just, getting the science done. And so if you're sitting there saying, I need you to build this fancy electrical system, we need to stabilize things, we know our room is oscillating around, you can do that, but you're never actually going to get to your science. And the laser labs that I grew up in, you'd spend the first 4 or 5 hours of every workday tuning the laser, trying to make it work, and then you spend the next 8 or 9 hours of every workday trying to do your science, which leads to no sleep, but hey, grad students are 21 years old, they can deal with that. But it also means that you only have about half the productivity. So if you can get this laboratory design right, you can be twice as productive, and you can do experiments that other people can't do. And in fact, we created some of the very first data that prove that biology makes use of quantum mechanics and manifestly quantum dynamics in its light harvesting. We created the first optical analog to MRI in our group. We created the first femtosecond chiral spectroscopy in our group. We can see things that no one else can see precisely because we have a laboratory environment that at the time no one else had, though now you guys build them around the country. Which I'm both excited and bitter about when it's all said and done. Should be honest about it, right? Okay.